So now we are going to cover chapter 14 exercises. There are 10 of them, and as usual, I have already scrolled to answers. Under answers, all of the questions are repeated in full, and then you have typed up answer. So first one, provide UPAC name of the product of the following reaction. And so here we have a reaction of 2-fluoro-3-methyl pentane with methoxide anion. So it will be something like sodium, typically sodium methoxide, maybe potassium methoxide. So in this case, we have methoxide anion that can act as a nucleophile or a base. Fluorine is the only leaving group here, and it's actually a poor leaving group. When a leaving group is poor, the only possible mechanism is elimination, and actually it has to be E2 elimination. In terms of mechanism, it has to be E2. And in case of poor leaving group, such as fluorine, in general with poor leaving group, regioselectivity is Hofmann. That means that less substitute double bond or less stable double bond is obtained as a major product. And so it has to be elimination, and the elimination could proceed in such a way to give us this 3-methyl, 1-pentene, or 3-methyl 2-pentene with double bond between carbons 2 and 3. It's going to be 1-pentene as a major product because it's a poor leaving group and it's Hofmann elimination. By the way, you have a summary of all of these reactions, so how different substrates react with base or nucleophile, what will be the mechanism, and outcome summary is on page 354. So this is obviously print, but you have it in PDF, so on page 354. It's just one page, very important summary, so make sure to know that really well, and hopefully make sure that you understand it, so that if there's more complex questions, you can apply that knowledge. But there may be some straightforward questions, simply like this. What is the mechanism? Next question, question number 2. Which of the following transition states results in formation of trans alkene? So here we have Newman projections of various transition states. If we are talking about transition state that leads to particular alkene, that means that it's an E2 elimination. Because in case of E1 elimination, we would be talking about carbocation intermediate that leads to formation of particular alkene. So you need to analyze each one to see which one would result in formation of trans alkene. And first one has bromine and hydrogen antiperiplanar. Bromine is obviously a leaving group. We identified bromine as leaving group. So it can undergo concerted elimination as carbon-bromine and this carbon-hydrogen at the back bond that are aligned, that are antiperiplanar. As they are broken, new pi bond or pi orbital is going to form there. So that's aligned properly for elimination. And you can see as this pi bond forms, these two substituents, two ethyl groups, are on the opposite sides. They will end up on the opposite sides of that bond. That's actually trans. So that's correct answer. Let's look at the next one. Now we have carbon-bromine bond, but what is antiperiplanar? What is aligned is carbon-carbon. Carbon-carbon bond cannot be broken in elimination reaction. So this one cannot actually undergo reaction. This one cannot undergo elimination. That also could be an exam question. Which of the four cannot undergo elimination? So that's the one. And then C. Now you again have carbon-bromine and carbon-hydrogen, just like A, properly aligned for elimination, antiperiplanar to each other. So breaking of these two bonds results in formation of pi bond. But now both substituents, both ethyl groups are on the same side of newly formed pi bond. So that's going to be cis. So C would result in formation of cis alkene. And finally, D is relatively rare mechanism, where carbon-bromine and carbon-hydrogen eclipse each other. They could undergo elimination. This one would be cis, but this is very rare mechanism because of the eclipsing of the substituents. This is eclipsing conformation. So it's high energy conformation, And this only occurs in certain cyclic systems when it's not possible for substituents to assume this anti-periplanar orientation. So this would be a rare mechanism. So correct answer is A. Question number 3 is variation on the previous question. Another way to ask this material. What is the product of an elimination that proceeds to the transition state shown below? And so now here we have a transition state. And so what's the product of the elimination? Well, carbon, bromine, and carbon hydrogen are broken. So pi bond is going to form there. And now when we consider what's the product, we have 1, 2 carbons. And then this dot, that's carbon closer to us, and a ring carbon at the back. So Newman projection represents 2 carbons. This dot, from which 3 bonds are projecting, closer carbon, and a ring over its horizon, 3 bonds are appearing. That's back carbon. That's 2 more carbons. And we see that newly formed double bond will be between carbons 3 and 4, because this is 1, 2, 3, 4. And we have 2 more carbons, 5 and 6. So it's going to be hexane, and it's going to be it's going to be hexene, 3 hexene. And so 1, 2, 3, this is 3 hexene, and this is 1, 2, 3 hexene. This is 2 hexene, and this is 2 hexene. So C and D are wrong. They are 2 hexenes. C and D would be correct if this first substituent were methyl and back one were propyl, or reversed. But okay, so it's A or B. So which one is correct? Well, we can see that as pi bond forms through breaking of carbon bromine and carbon hydrogen bonds, 2 substituents end up on the same side. That's cis, which means that B is correct answer. So 3B. Okay, let me see if there are any questions. No questions? Okay. Okay, question number 4. Which of the following bases favors a Hofmann elimination reaction? That's going to be a base that is hindered, that is rather large, rather hindered base, because steric hindrance in general favors Hofmann elimination. And so sodium isopropoxide, that's actually pretty hindered, so that could be correct. Potassium hydroxide is very small, that's not hindered. Same as methoxide, that's not. And last one, sodium amide, it's very strong base, amide, but again not hindered. All of these have very small substituents. Nitrogen is the basic atom, the atom that will pick up a proton, but substituents are hydrogens, that they don't offer any steric hindrance. In this case, methoxide, it's oxygen with methyl group. Methyl group, again, not much steric hindrance. And hydroxide, OH, again, no hindrance. Isopropoxide, that's the one. That's the one that is hindered. So that's the one that favors Hofmann elimination. So 4A. So it's one of those cases where you're looking for the best possible answer. So you're comparing these 4 and you're looking which one is the most hindered. That would be Hofmann. Question number 5. What is the product of E1 elimination of trans 1-bromo-2-methyl cyclohexane upon heating in metal? So E1 elimination means that intermediate is carbocation. And so here you have 4 possibilities. So the best is to write down first starting material. This is trans 1-bromo-2-methyl cyclohexane. Upon heating in methanol, bromine leaves to give the intermediate carbocation. Actually, there is a rearrangement which is missing. I'll fix it right now. So in the course of reaction, although in this case actually it's not really important, but a rearrangement occurs because it's a secondary carbocation, and so it will rearrange into a tertiary. So this is correct. So as you can see, secondary carbocation forms through leaving of bromine, and then proton shifts or hydride shifts, H minus shifts, to give tertiary carbocation. And now loss of proton gives actually the most stable alkene, because in E1 elimination, the most stable, that means the most substitute alkene, is obtained. And in this case, B is the most substitute. It's inside the ring and has 3 substituents. A would have been without rearrangement and only 2 substituents, and also C could form from this cation, but only 2 substituents, and that's rather unstable double bond outside the ring. D is not possible, it has 2 double bonds. So B is correct answer. Question number 6, similar but a little bit more complex. What is the major product of the following elimination reaction? So in this case, again, we have heating in methanol, but now you need to figure out that this is E1. You know that this is E1 because base, methanol is weak base. Weak base favors unimolecular reaction, the same way as weak nucleophile favors unimolecular reaction, SN1 over SN2. So in this case, weak base favors unimolecular elimination, E1 over E2. Conversely, strong base favors E2 and strong nucleophile SN2. And you will recognize strong base, strong nucleophile the same way. Usually you're looking at the charge. The only difference is that base is not sensitive to steric hindrance. Nucleophile cannot be strong if it's hindered, and if it's very hindered, it's not nucleophile at all. For base, that doesn't matter. Steric hindrance does not affect base strength. In fact, sometimes a lot of substituents will increase base strength. So this is weak base, therefore intermediate is cation, and cation is going to rearrange its secondary carbocation, so methyl shift will result in rearrangement. And now, what are the possible products? Well, from this carbocation, the possible products are shown in blue and red. So red is less likely because that gives less stable, what we call exocyclic double bond. Only disubstitute double bond with double bond outside the ring. That's unstable double bond. This pathway shown in B is actually correct answer. Tetrasubstitute double bond. And note that this carbocation is symmetrical. So removal of hydrogen from the other side gives the same product. See, formation of double bond here. It's the same product. So B is correct answer. And if you want to name it, you would name it 1, 2, 3 trimethyl cyclohexene. Question number 7, that's what I just told you about that page from the textbook. I believe page 2. Okay, don't want to guess it. 354. So you would apply that knowledge. And in general, you'll be looking at material from that chapter, but that's where it's summarized. So what is the mechanism of this reaction? So first, when you look at substrate, which is the first thing you're looking at, it's secondary. So it could be anything. Because if it's primary, it has to be SN2. If it's tertiary, it could be E1, E2, or and SN1. E2 tertiary substrates readily undergo E2 elimination because E2 elimination is not sensitive to steric hindrance. Proton is removed from different carbon, not from hindered carbon, but one next to it. So tertiary substrate could undergo anything except for SN2. Secondary substrate could be anything of this form. And by the way, alkyl fluoride is only E2. That's that summary from that page. So um, so here, consideration of substrate, it's secondary, doesn't help you because any of this, you cannot eliminate any mechanism. Now, next you're looking what kind of reagent you have. So this reagent, like most reagents like these, in these reactions, is both a base and a nucleophile. But is it strong or weak? It's strong because it's sodium methoxide. There is negative charge on oxygen. It's both a strong base and a strong nucleophile. Since it's strong, it favors bimolecular reaction. So reaction mechanism is going to be either E2 or SN2. That's going to be competition. It's not going to be unimolecular. If it was, let's say, methanol, then it would be unimolecular, and you would consider whether it is E1 or SN1. But in this case, obviously, it's bimolecular because it's strong base, strong nucleophile. And then the only question is it E2 or SN2? And that's where reaction temperature tells us. Low temperature favors SN2. High temperature, E2. With heat, that means E2. And so mechanism is E2. So as you can see, it's systematic approach. You have to consider all these factors one by one and eventually come up with mechanism. Another question, same topic. What is the mechanism of the following reaction? And now we have tertiary substrate. So with tertiary substrate, as I just said, you can eliminate SN2. It cannot be SN2, but it would be any of these three. And now base or nucleophile is ethanol. That's weak base, weak nucleophile. That means mechanism is unimolecular. So it's either E1 or SN1. And again, finally, you have to look at the temperature. Low temperature is again going to favor substitution, high temperature elimination. And since this is high temperature, then mechanism is E1. And let me just see it. Yeah, this is not correct. Okay. This is weak. Yeah, let's see. Yeah, I don't know why if I made this mistake. Okay. I'm fixing it now. Unimolecular. Unimolecular. And so reaction mechanism is unimolecular. Reaction mixture is heated, and that favors elimination. So which means that reaction mechanism is AE1. Okay, so fixed. Okay, let's see if there are any questions. Okay, no questions. So final two exercises are a little bit different. They involve multi-step questions. So what is the product of the following reaction sequence? Multi-step and also require knowledge from different chapters. So you're being tested on knowledge from more than one chapter. So what is the product of the following reaction sequence? And so first you have a reaction of 2-bromo, 1,1-dimethyl cyclohexane with methanol with heat. And then after that reaction is over, treatment with osmium tetroxide and N-methyl morpholin oxide. So first step is E1 elimination. because methanol is weak base and reaction is carried out with heating. So E1 elimination. And E1 elimination proceeds to carbocation as reaction intermediate, which means that upon rearrangement, product is 1,2-dimethyl cyclohexene. And then you need to know from chapter 9 that osmium tetroxide, catalytic osmium tetroxide, with N-methylmorpholin oxide as stoichiometric oxidant results in cis hydroxylation of double bond. So two hydroxyl groups are added from the same side of the double bond. And so that's the product. On the test, this would be a multiple choice exam with multiple choice question, and you would need to pick this answer. Question number 10. What is the product of the following reaction sequence? So now we have 3-step reaction, but again, it requires only knowledge of 2 chapters. You will see in a minute how. So this is a reaction of dibromide. This is a geminal dibromide. Both bromines are on the same carbon. That means geminal. And reaction with strong base, potassium hydroxide, at high temperature, 170 degrees Celsius, means that 2 molecules, 2 equivalents of HBr are eliminated to give terminal alkyne. If reaction were with potassium hydroxide at room temperature, then only 1 equivalent would be eliminated, and we would end up with final bromide. High temperature, 170, that means you get alkyne. And then these 2 steps, actually second step, sodium amide, that's deprotonation of terminal alkyne to give acetylide. And finally, step 3, that's either chapter 10, these steps 2 and 3, that's either chapter 10 or 12, depending how you look at it. Either a reaction of alkynes or SN2 substitution. So now we have SN2 substitution where acetylide anion as a strong nucleophile displaces bromine in bromocyclohexane to give this final product. Okay, so this completes exercises related to chapter 14, so 10 chapter 14 exercises. And at this point, I'm going to stop recording, and then after that, I will answer any questions you may have.